Okay. Thank you so much for the introduction. So today my talk will be quantum uncertainty principle for measurement with interventions. So this is a joint work with Xiao from University of Hong Kong, Wang Ximing, Liu Qing, and Miller.
No, you have to press your desktop. It's not clear.
Okay.
Yeah, just a pointer.
So let's talk about the take-home message first. Assume we have a multiple choice question, and classically, if we remove the possibility to be A, we will still need to figure out whether the answer should be B or C. It's like this one. But quantum mechanically, if we remove the possibility to be A, sometimes the answer A will be correlated with B. So we know the answer can only be C. So this is the main topic of today's talk. Nowadays, people are seeking quantum advantage. At this moment, you will feel disappointed because I'm trying to talk about the typical quantum disadvantage uncertainty principle. So in classical world, if we have a football, it's very easy to measure both its position and momentum. But in quantum world, we know given a free particle, it's impossible to know its position and momentum at the same time. So this is a well-known uncertainty principle. And this form is given in the year 1927. Okay, based on different forms, we will have different kind of uncertainty relation. Like we can use standard deviation to quantify the uncertainty principle, and we can also use entropy to quantify the uncertainty. And even for the formation, we can divide it into like a product form or summation form. Like each observable can be equally distributed or weighted. Moreover, we can also consider the form whether we have quantum memory or no memory. Actually, even back to the year 1935, the original EPR paper is talking about the uncertainty principle in the principle of quantum memory. Albert Einstein tried to beat the completeness of quantum mechanics by using the example of uncertainty principle. So if you are interested in this topic, you can find so many wonderful papers online. I do not have enough space here, so I just show some result here along the line. And uncertainty principle is very important because it has lots of applications ranging from witnessing quantum correlation cryptography and more application in engineering. Like we can consider about using uncertainty principle to understand metrology sensing, and we can further using uncertainty principle to investigate the programmability of quantum processor. Actually, this is a work under preparation, and we will try to submit to archive next year. Okay, but till now, all these uncertainty relations are only passive measurement. That means when we try to understand some property of a quantum system, we simply wait until we do measurement. This kind of passive measurement include all previous results, like standard deviation form, like the standard Mason-Wolfing uncertainty relation, and like the uncertainty principle in the principle of quantum memory, like this form. And the last one introduced by Gillard, this is universal uncertainty relation. It applies to probability distribution between different observables. So sorry, the relation here should be majorization. It's a typos here. But the most general and powerful way of learning from quantum system is interactive measurement. That means even for a toddler who try to understand her environment, she will try to do some intervention, like implement action, observing resulting reaction, and do further action based on observation. Then how can we translate this kind of interactive measurement into quantum system? That's the main topic of today's talk. So here, we start with some examples. The first one is so-called pseudodensity operator introduced by Professor Velakov from Oxford. The idea is like we try to understand the quantum system and its evolution in the future. Now we can choose some quantum instrument like Pauli measurement, do the measurement, and choose the output as an input to the B system. And after the evolution inside, we implement another projective measurement, which can be Pauli measurement. Then based on the outcome x1 and x2, we can build the so-called pseudodensity operator. And it can be implemented into different areas like teleportation and other topics. But actually, in the year 2015, this kind of idea, okay, even though it's not called pseudodensity operator, has also been applied to investigate causal inference. So this is Rose-Beckman's work. It has been used to infer causality associated with causal map. And further, it is also related to the coherent mixture of causal relations. But the quantum dynamic that has been investigated is not in its most general form. For example, like here, we only consider about the initial state and the later evolution here. But more generally, there may be some quantum environment allow initial state to be correlated with the evolution happening later. And moreover, we can also use ancilla system to help us build the most general form like this. Consider some quantum channel here and using ancilla to correlate it with the later quantum measurement. But more generally, the most general form of quantum dynamics should be a non-Markovian quantum process. Okay, it has multiple names like quantum strategy, quantum cones, or even process tensor. But it has been used to describe the Markovian quantum dynamic. And the most general form of measurement is like this one. We can implement some quantum channel lambda 1 here until lambda a minus 1, and then implement some POBM as an end. We call this kind of measurement as interactive measurement. Okay, this kind of interactive measurement is very important. The motivation comes from two parts. Part one is like the system will evaluate all the times because there's a Hamiltonian, and the quantum state, the fixed moment, doesn't never exist because time flows. Okay, so we need to generalize uncertainty principle from state case to quantum channel case. And this is a work with Gila together. We introduce uncertainty principle of quantum processes. Another side is like, actually this kind of interactive measurement will play an important role in lots of applications, ranging from quantum illumination, quantum enhanced aging, and non-Markovian open system. Now let's talk about the trade-off between two incompatible interactive measurement. We can using a guessing game to explain the uncertainty relation. It's like Alice has two different interactive measurements, and Bob can prepare any non-Markovian quantum dynamic. They will interact several rounds, and then Bob will guess the measurement outcome. So here, Bob knows the interactive measurement Alice have, like T1 and T2. But before the measurement has implemented, Bob does not know which one will be implemented. And assume Bob has like K bets. Each round, for example, like the first round, Bob only has one bet. So Bob can only put one bet on this table, only choose one to put the bet. Okay, for the second round, if Bob has two bets, do the same game again. But here, Bob can choose another quantum dynamic. Okay, I have to give a remark here. So in different rounds, Bob can prepare a different quantum dynamic to maximize his winning probability here. So connect all the successful probability together, Bob can create a vector. This vector can bend the uncertainty associated with interactive measurement T1 and T2 by using majorization. So this is a majorization. And definitely this vector V depends on the interactive measurement prepared by Alice, but has nothing to do with the initial quantum dynamic prepared by Bob. Okay, getting this majorization uncertainty ratio in vector form, that's not enough because we cannot say this is optimal band for uncertainty ratio. Because when we rearrange all the probability distribution in non-increasing order, the probability simplex becomes a majorization lattice. And this majorization lattice is complete. So we can always find this upper band and lower band. By applying some non-negative Shor concave tension, we can obtain infinitely different forms of uncertainty ratio. So that's why this kind of uncertainty ratio is also called universal uncertainty ratio. This is a paper, majorization lattice is complete, has been proved. And from this paper, you can derive another process called Sonatalis process, which will lead to the optimal band. And from this paper, remark 2, this book, you can know why entropies can reverse the order and obtain the entropy uncertainty ratio. Okay, once we have the uncertainty relation for interactive measurement, let's try to talk about its application. So we try to build the connection between uncertainty relation and causal inference. So according to common cause principle, we know the causality associated with different events, two different events belongs to three different categories. The first one is direct cause, and the second one is common cause. You can see the causal diagram on the right-hand side. And the last one is mixture of direct cause and the common cause. When we try to translate the language of causal diagram into quantum dynamic, we have the following example, like this one. We have some initial state. Okay, this initial state has nothing, will not be related with the upcoming quantum dynamic sign. So inside the blue box is a quantum dynamic we try to investigate. Then the event, the operation we implement here between system A and system B will definitely influence the result of C. For example, like we have an identity chain here. No matter what we prepare will become the output of this system C. On the other hand, we can prepare a maximum entangled state, and here we trace our system B. Then the measurement outcome happens here, the system A. We have some correlation with measurement outcome related with system C, because we can prepare a maximum entangled state here. But moreover, we can choose some suitable pre-processing and post-processing. So here, this kind of quantum dynamic has a special name called causal map. It's a special case of super channel, which is pre-processing, does not have a input system. If you are not familiar with the language of super channel, it's still okay. For example, like if you're trying to transmit quantum information, it contains two different processes. The first one is encoding, the second one is decoding. So if you are familiar with error correction, then you can think about this as encoding and this as decoding. Just like in quantum system, we allow the causal map has no input for encoding. Okay, in order to gain the causality associated with causal map, we try to design two different indicators. So the first one is interactive measurement, TCC. This is a so-called common cause indicator because if the measurement outcome happens with certainty, then we can state that the quantum dynamic can only show common cause. Okay, for the second indicator, interactive measurement, TDC, if the measurement outcome happens with certainty, then we can state the quantum dynamic can only show direct cause between event X and event Y. So these are two different interactive measurement. And moreover, trying to build the trade-off between these two different interactive measurements. This is not the same as the previous uncertainty relation because we try to build a fundamental trade-off between two families of uncertainty relations. Here, we never fix the unitary gate U1 here, and we never fix the unitary gate U2 here. So it depends on U1 and U2 chosen here. And similarly, here we have our freedom to choose different U3 and U4. And for these two different families of uncertainty relation, two different families of interactive measurement, we can build its fundamental trade-off. So in order to complete this task, we can try to do some trick here. We can observe the unitary gate inside the causal map and change the quantum dynamic at the same time because we try to minimize the uncertainty over all quantum causal maps. So this step is allowed. By using this trick, we derive the following causal uncertainty relation. So for example, like when we consider this kind of quantum therapy, okay, so here the initial state is maximum entangled state, and this Z is a rotation along Z direction, and this X is rotation along X direction. Now the uncertainty has been shown here. This is blue curve is uncertainty relation associated with two different interactive measurement, and the plane is the lower band. So through this diagram, it is easy to see our band is tight. Okay, tight does not mean optimal. For example, like for Massey and Wolf's uncertainty relation, we know the lower band is minus log C1. C1 stands for the maximum overlap between two different incompatible measurements. But this band can be improved by considering the second largest overlap between measurements. And the uncertainty for common cause.
Very uncertain like that.
Yeah.
Well, this is extended period.
Okay, thank you.
What did you do?
We have shown the uncertainty of common cause and direct cause here, and this lower band is also shown inside this diagram. Okay, now I'm trying to answer why this kind of causal uncertainty relation can be used to do causal inference. For example, like for qubit case, we figure out for indicator of Dirac cause and common cause, the lower bound is 2, and this is optimal. And then if we implement the indicator of Dirac cause and obtain its entropy is equal to half, then it cannot be Dirac cause because the indicator of Dirac cause is if and only if condition for the quantum dynamic to be Dirac cause. If this is a pure comp, that means the rank of the Chou operator is 1. Then from this uncertainty relation, we know the entropy of common cause is greater than 1.5. That means it cannot be common cause at the same time. Okay, that means when we remove the possibility to be Dirac cause, it can also not be common cause. And the answer can only be the mixture of Dirac cause and common cause. That's why causal uncertainty relation can be used to do causal inference. And let's compare with previous criticals. So actually, you can see here for different parameters, we can use causal uncertainty relation to investigate the causality associated with different parameters, except for the point shown here, like the yellow dots and the green one. Besides these dots, you can figure out its causality. And given a quantum dynamic, if you try to use tomography to investigate its causality, it will require DQ, different measurement. If you are trying to use pseudo-density operator, it will require d power of 2. But remember, even though you can use tomography to rebuild the Chou operator of this quantum dynamic, it does not guarantee you can understand its causality because you still need to prepare some method to infer causality associated with quantum dynamics. And if you implement causal uncertainty relation, then a simple measurement is enough. I have already showed the example. Now let's come back to take-home message again. So classically, when you remove the possibility to be Dirac cause, you still need to figure out whether the causality is a common cause or mixture. That's classical critical. But in quantum mode, when you remove the possibility to be Dirac cause, sometimes you will also remove the possibility to be common cause. Because there's a fundamental trade-off between Dirac cause and common cause. Then the answer must be a mixture of Dirac cause and common cause. Okay, let's make a short conclusion. So here we know there's a typical quantum disadvantage uncertainty relation, and we try to build the quantum disadvantage with causal inference by building the so-called causal uncertainty relation, which transform the quantum disadvantage into quantum advantage. And moreover, if you try to look up all the details, then we prepare a short paper. You can figure out here, and it's non-expert friendly. But if you try to understand all the mathematics and technical, we also prepare some 47 pages supplementary material, which is experts unfriendly. Thank you.
Questions? I have one. Yeah. So I was wondering, there are all of these kind of interesting, non-trivial mixtures of Dirac cause and common cause, coherent superposition versus just like a classical mixture.
Yes.
Does your framework provide any insight into the differences between those?
Okay, very good question. Actually, we also try to distinguish between like pervasive mixture of Dirac cause and common cause or coherent mixture, but we do not get any useful result yet because in classical world we only have pervasive mixture of Dirac cause and common cause, but in quantum world, this paper has shown the coherent mixture of Dirac cause and common cause. Let me show you. Yeah, this one. This one also shows the coherent mixture of Dirac cause and common cause. Yeah, maybe in the future we will try to figure out how to use authentication to distinguish between pervasive mixture and coherent mixture. By the way, causality here we only mean the causal structure. I never mean like quantum switch process, matrix, indefinite causal order, this kind of stuff. But indefinite causal order like quantum switch has been implemented to improve the band or improve the performance of quantum metrology by Xiao Yang and not only one paper, several papers already. And is there any band that a new authentication for this kind of entropy, for this kind of metrology? Yeah, we are also thinking about this. Thank you.
Thank you for that. Any more questions? Yes.
You consider these operations with no causal order in this paradigm?
Yeah, good question. Yeah, we try to build such authentication, but no clear result yet. Yeah, because if we only focus on process matrix, we can formulate something. But what's the physical meaning of that authentication, and can we use this authentication to achieve some advantage? That's another question, and we cannot provide any useful answer till now. We try to do that because metrology can be improved by using quantum switch. Is there any authentication associated with this? That kind of metrology is a good question. We are working on that.
Any more?
And I use it to sort of detect source of the error or noise in my processor, like whether there's a mediating channel, and whether the error is being mediated through an external environmental coupling.
Yeah. Good question. Actually, we are also thinking about extend sequential authentication to this kind of form and try to use sequential authentication to investigate whether there exists quantum memory between initial state row here and the side here. We are working on that.
I believe with this causal inference, we should be able to detect.
Yeah, because
the
to the best of my knowledge, if there's no quantum channel side here, and we prepare some initial state and implement two different sequential authentication, then there's no fundamental difference between sequential authentication and special authentication for state case. This has been investigated in the paper of Krauss published in PRD paper in the year 1987, which is called Krauss conjecture for ring entropy satisfy some condition like 1/alpha plus 1/beta, which is equal to 2. This is a harmonic condition. Then there's a so-called Martin-Wolfing acceleration, which has been proved in the next year, 1988.
Any more?
I'm just wondering if you know by any chance if there's any work being done on relationship between this interactive uncertainty relation and cryptographic protocol and interactive matters such as bit commitment or coin flipping?
To the best of my knowledge, no.
Okay, all right, thanks.
Any more? Okay, I guess we'll move on.